Hi everyone, it's Sorkin. Today we are going to take a look at the backtracking. So first let's take a look at what is backtracking. Backtracking is a method for finding all possible solutions to a problem and the backtracking whenever a path fails to work. So for example, let's take this example. We are given an array of these distinct integers and we need to return all possible permutations. So for example, let's say that our input is 1, 2, 3 and we need to return for 1, 2, 3 all possible permutations. So the first permutation is the input itself 1, 2, 3. The next one is 1, 3, 2 and the next one is 2, 1, 3 and so on. So in total we have 6 permutations for our input. So how we are going to solve this problem? We are going to solve this problem using backtracking. So for the backtracking, so what we do first is we are defining our base case. In our case, the base case is that if our size of our temporary array, if that equals to our input size, then in that case we are backtracking from that branch. So for example, let's say that for our first element, right, so we are generating a tree of all possible permutations. The first element we are adding 1, 2, so we are adding 1, 2, and the next one is we are adding 1, 2, 3. So we are backtracking because the size of our input, because the size of our temp array 1, 2, 3 in this case is equals to our input size. Now we are going to the next one. So now we're considering the next element, which is 1, 3, and in this branch, so we are adding the element that is missing here, which is 1, 3, 2, and we are backtracking from this branch. So we have generated all possible permutations starting from 1. Now we are doing that exactly the same starting from 2. So starting from 2, we are considering the first element 2, 1. So the next element we are skipping 2 because 2 is already in our permutation. 2 is already here, so we are going to the next element, which is 3, right? So 2, 1, 3, and we are backtracking from this branch. So the next one is that the next element is we are skipping again 2, we are going to 3, so we are going to 3, and the next element that is missing here 1, so our next permutation is 2, 3, 1. So we have again generated all possible permutations starting from 2. Now we are going to the next element, which is 3. For 3 we are doing exactly the same, so we are generating 3, 1, 3, 1, 2, and the next one is 3, 2, and the 3, 2, 1. So the code for the above is, so what we do is we are creating a result and a rate where we are adding all our permutations, and we are calling our backtracking function. So in our backtracking function, our base case is that we are checking that if our temp list, if the length of our temp list is equals the size of our input array, then in that case we are adding that to our result. If not, then what we do is we are checking that if that num is already in the template, so which means that we need to skip that, we have already added that. If it's not, then in that case we are adding that to our temp list, and we are recursively calling our backtracking function. And at the end, as we are backtracking, we are cleaning from our temp list, so we are popping, which means that we are cleaning the elements that we have added in that branch. So this is for the case when our size is equals to, our base case is equals to our base case is when our size is equals to the input size. So let's change our base case. Let's say that our base case now is that we need to find all permutations when the size is equals to 2. If the size is equals to 2, so what we do is in this case we are starting to backtrack when our size of our temp list, right, is equals to 2. There is no need to go further and explore the other options because this is our restriction now. This is our base case now. So how we calculate the time complexity for the backtracking? So in this case, we have nums 1, 2, 3, right? At the first, if we are at the first position, so if we are, our first choice is that we can we have three choices. So we can either choose 1, 2, or 3, right? So we can start from any of these elements. So we are choosing 1, and then now we have options for the next one. We have options 2 or 3. So for the position 2, for the second choice, we have how many choices we have? We have 2 choices. We can either choose 2 or 3, right? So we can choose 2 or 3. So for example, we are adding 1, 2, and we are for the next choice, we have only, for the next position, we have only 1 choice. And for the position 3, for the third choice in our case, right, we have only 1 choice for the final position. So we have 1, 2, 3, for example. And if we calculate our time complexity in this case, that would be that in the first position we have 3 choices, so 3 multiplied by 2. In the second position we have 2 choices, and the last one we have only 1 choice, so 3 multiplied by 2 multiplied by 1, which means that if we generalize that, so that would be that the n multiplied by n minus 1 multiplied by n minus 2 and so on. So that gives us n factorial. So the time complexity of this solution is n factorial. So for example, in this case, the starting with 1, so we have two permutations. Starting from 2, again we have 2 permutations, and starting from 3 we have also two permutations. So 3 multiplied by 2 multiplied by 1 gives us 6, which is our n factorial. So when we should use backtracking, when to use backtracking, we are using backtracking in cases when we need to any problem. So everything that starts with the generate all with some constraints. So for example, let's say that for generating permutations, for generating combinations, subsets, for n queens, let's say that the n queens problem where we need to position 4 queens in a chessboard and not to have any of the queens under attack. So for the Sudoku problem, for the crossword puzzles, for the maze solving, for the grid-based navigations, for example, for equal subset sums problem, palindrome partitioning, and so on. So we can use backtracking. Any case where we need to generate all possible options with some constraint. And if, for example, the problem is that any problem where we need to generate all possible solutions, path, partitions, and the backtrack if solution is found, or if no solution exists in that branch. So we are defining our base cases. If our base cases is not, if we hit those base cases, then we are starting to backtrack from that branch. So what are the disadvantages of using backtracking? Disadvantage is that usually in backtracking we are getting the worst time complexity, which is that either we get that it's exponential, it's either to the power of n or n power of n, for example, or it's n factorial, that as we have seen earlier, right? So that and we end up sometimes solving the same problem repeatedly. So we are solving in the different branches, we are solving the same problem. So how we usually improve the backtracking is that we are using a dynamic programming. So let's say that if in some branches we keep solving the same problem that we have solved earlier, we are storing the solution, we are storing that solution we are using a memoization in dynamic programming. So it's basically a cache. So we are storing our previous solutions in the cache to use them later, not to generate the same branch, not to generate the same solution in another branch. So if we have already generated the answer for that branch, for the similar branch, so we are storing that and we are reusing those solutions later. Okay, that's it for today. Hope you like my content. If you like it, please hit the like button and subscribe my channel. See you next time. Bye.